A diode is a small two-terminal electronic component. You'll usually see it as a tiny black body with a white stripe on one end. Its schematic symbol shows the direction of conventional current flow. At its core, a diode works like a one-way valve for electricity. It allows current to flow in only one direction. The white stripe marks the cathode, and conventional current flows from the anode to the cathode. Let's look at a simple circuit. We know that conventional current always flows from positive to negative. If we place a diode in the circuit so that its arrowhead points in the same direction as the current, nothing really changes. When we turn on the switch, the bulb lights up normally. Current flows just like before. This condition is called forward bias. But what if we flip the diode around? Now the arrowhead points against the direction of current. When we turn on the switch, the bulb does not light up. That's because the diode blocks current flowing in the opposite direction. This condition is called reverse bias. This behavior may seem simple, but it turns out to be extremely useful. One common use of a diode is polarity protection. If a power supply is connected the wrong way around, the diode blocks the reverse polarity and protects the circuit. Diodes are also used for rectification, converting AC into DC. A single diode gives half-wave rectification, while 4 diodes in a bridge provide full-wave rectification with a smoother DC output. Zener diodes are used for voltage regulation. They clamp the voltage at a specific level by conducting in reverse once a set threshold is reached. Diodes are also used as flyback diodes with motors and relays, absorbing voltage spikes when these devices switch off and protecting the rest of the circuit. There are many applications of diodes, and we'll explore them one by one in future videos. For now, let's focus on the basics of how a diode behaves. To do that, we need to look at the voltage-current relationship of a diode. Here's a simple test circuit. We use a variable voltage source, and our goal is to measure two things: the voltage across the diode and the current flowing through it as we change the voltage. For this, we use a voltmeter and an ammeter. As we vary the voltage, we record the voltage across the diode and the current through it, and then plot these values on a VI graph, with voltage on one axis and current on the other. At the beginning, the source voltage is 0. That means the voltage across the diode and the light bulb is also 0. We start at 0 volts, and as expected, there's no current flowing. Even as we slowly increase the voltage, we still don't see any noticeable current. This continues until we reach about 0.7 volts. Once the voltage reaches roughly 0.7 volts, something interesting happens. After passing this point, the current increases very rapidly, almost as if the diode has suddenly turned into a closed switch. At this stage, we say the diode is forward biased. To forward bias a typical silicon diode, about 0.7 volts must be applied in the correct polarity. This voltage is called the knee voltage, or cut-in voltage. It's the minimum voltage at which the diode begins conducting heavily, and the current rises quickly. Now let's reduce the voltage and reverse the polarity. On the negative side of the graph, we need a much larger voltage range than on the positive side. No matter how much reverse voltage we apply, almost no current flows. The diode behaves like an open switch. This condition is called reverse bias. If we keep increasing the reverse voltage even further, the diode eventually reaches its limit. At a certain point, it suddenly begins to conduct. This voltage is called the breakdown voltage. After breakdown, the diode no longer behaves like a one-way valve. So this graph shows the basic VI relationship of a diode. When a forward voltage is applied, the diode behaves almost like a closed switch once it passes the knee voltage. When a reverse voltage is applied, the diode behaves almost like an open switch up until it reaches the breakdown voltage. For normal diodes, reaching this breakdown voltage usually destroys the device. But for Zener diodes, this breakdown region is intentionally used to produce a constant regulated voltage. Also keep in mind that even in reverse bias, a very small leakage current can still flow. Now we have a good idea of how a diode behaves. The next question is, why does it behave this way? To answer that, let's explore what's actually happening inside the diode. Even though a diode looks like a small black component on the outside, inside it's not just two wires touching. It's actually a single continuous silicon crystal. One side is made p-type and the other side is made n-type. The boundary where these two regions meet inside the crystal is called the p-n junction. To understand this structure, we first need to know what a semiconductor is. Semiconductors are materials that normally behave almost like insulators. Under normal conditions, they conduct very little current, but their conductivity can change quite easily. For example, a semiconductor's conductivity can change with temperature, light, mechanical stress, or electric and magnetic fields. Because of this special behavior, semiconductors sit between conductors and insulators. Common semiconductor materials include silicon, germanium, and gallium arsenide. Among these, silicon is by far the most widely used material in electronic devices, including diodes. Let's take a closer look at a single silicon atom. It has 14 electrons, but the ones that matter for conductivity are the 4 in its outermost shell. These are called valence electrons. In a pure silicon crystal, each silicon atom shares these 4 valence electrons with 4 neighboring atoms, forming covalent bonds. This creates a very stable, tightly bonded lattice. Because all of the valence electrons are locked into these bonds, they can't move freely through the material. That's why pure silicon behaves almost like an insulator. However, when we apply heat, some electrons gain enough energy to break free from their bonds. Once free, they can move through the crystal and carry electrical current. This temperature-dependent behavior is a key feature of semiconductors and is what allows them to be so precisely controlled in electronic devices. There's another, even more efficient way to make silicon conductive. Let's consider phosphorus, an element with 5 electrons in its outer shell. When a phosphorus atom is introduced into the silicon lattice, it forms 4 covalent bonds with neighboring silicon atoms, just like silicon does. But here's the key difference. That 5th electron has no bond to join. It's left over, loosely held and free to move through the crystal. Now imagine this happening across an entire silicon wafer with millions of phosphorus atoms scattered throughout the lattice. Each one contributes a free electron, and even without adding extra energy, these electrons are ready to move. The result is a silicon wafer that conducts electricity far more effectively than pure silicon. With just a tiny change at the atomic level, we've transformed nearly insulating silicon into a precisely controllable conductor. There's another fascinating way to increase silicon's conductivity, this time by adding atoms that don't have enough electrons. Let's consider boron, which has only 3 valence electrons. When a boron atom is introduced into the silicon lattice, it's surrounded by 4 neighboring silicon atoms, each trying to form a bond. But with only 3 electrons to offer, one bond remains incomplete, creating a missing electron. Since electrons carry negative charge, this absence behaves like a positive charge. We call this missing electron a hole. But here's an important point. A hole isn't a real particle. It's simply a vacancy, a place where an electron could be. That hole doesn't stay in one spot. Nearby electrons can jump in to fill it, and when they do, a new hole is left behind where the electron came from. So even though only electrons are actually moving, it appears as if the hole itself is moving in the opposite direction. Now, imagine this happening throughout an entire silicon wafer, with millions of boron atoms spread across the lattice. Each one contributes a hole, and even without adding extra energy, these holes are ready to move. The result is a silicon wafer that conducts electricity far more effectively than pure silicon. Now, let's compare the types of semiconductors we've discussed. We start with a pure semiconductor crystal. This pure material is called an intrinsic semiconductor, and on its own, it conducts very poorly. When we deliberately add small amounts of specific atoms to increase its conductivity, the material becomes an extrinsic semiconductor. The process of adding these impurity atoms to an intrinsic semiconductor is called doping. Now pay close attention to these two extrinsic semiconductor materials. In one case, silicon is doped with phosphorus. In the other, silicon is doped with boron. Even though both materials conduct electricity, they do so in very different ways. To keep things clear, let's focus only on free electrons and holes, because these are the charge carriers responsible for conductivity. When free electrons are present, we can see electrons moving through the material. Since electrons carry negative charge, this type of material is called negative type, or N-type. In the other case, we have holes. Here, electrons don't move freely through the lattice. Instead, they hop from atom to atom to fill these empty spots. This makes it appear as if the holes themselves are moving in the opposite direction. Because we treat holes as positive charges, this material is called positive type, or P-type. In an N-type semiconductor, the majority charge carriers are electrons. In a P-type semiconductor, the majority charge carriers are holes. Now, the real magic happens when we bring an N-type and a P-type semiconductor together. At first, you might expect that since both materials conduct electricity on their own, connecting them would simply create a normal conductor, one that allows current to flow easily in either direction. But that's not what happens. To understand why, we need to look closely at the interface where these two materials meet. The interface where these two materials connect is called the p-n junction. So what actually happens around this junction? Near the junction, free electrons from the N-type region move into the P-type region and fill nearby holes. As this happens, the area around the junction is left with no mobile charge carriers, no free electrons, and no holes. This region is called the depletion region. It behaves like pure silicon, meaning it does not conduct electricity under normal conditions. But there's something else important happening at the same time. When an electron leaves the N-type side, that region loses a negative charge and becomes slightly more positive. When that electron enters the P-type side, it adds extra negative charge there. This separation of charge creates an electric field at the junction. That electric field makes it harder and harder for additional electrons to cross from one side to the other. With each passing electron, crossing the junction becomes more difficult. This growing resistance to movement is called the potential barrier. The result is an internal voltage across the junction, like a tiny battery between the P-type and N-type regions. As we've seen, a diode can be either forward biased or reverse biased. Now let's take a closer look at what actually happens inside the diode in each of these two configurations. Let's start with forward bias. In this case, the negative terminal of the battery is connected to the N-type side, and the positive terminal is connected to the P-type side. The negative terminal pushes electrons in the N-type region toward the junction, while the positive terminal pulls electrons away from the P-type region. As electrons leave the P-type side, new electrons enter the N-type side at the same time. This gradually reduces the potential barrier at the junction. Bit by bit, the depletion region becomes thinner. At a certain point, the external voltage completely cancels the internal barrier. The minimum forward voltage needed to do this is called the knee voltage, or cut-in voltage. Beyond this point, the diode behaves almost like a normal conductor, allowing current to flow easily. Once the barrier is removed, electrons from the N-type region can cross the junction and move into the P-type region without difficulty. This configuration is called forward bias, and it directly explains the forward portion of the diode's VI curve. Now let's look at reverse bias. In this case, the negative terminal of the battery is connected to the P-type side, and the positive terminal is connected to the N-type side. The negative terminal pushes electrons in the P-type region toward the junction, while the positive terminal pulls electrons away from the N-type region. As electrons are pulled away from the N-type side, electrons entering the P-type side recombine with available holes. This increases the charge separation at the junction, making the potential barrier stronger and the depletion region wider. Even though electrons may enter the P-type region from the external circuit, they simply recombine with holes and cannot cross the widened depletion region. As a result, no current flows through the diode in this configuration. So in reverse bias, the barrier potential opposes the supply voltage and effectively balances it. As the reverse voltage increases, the internal barrier continues to grow. For a normal diode, if the reverse voltage becomes too large, the junction can no longer withstand the strong electric field. At that point, the diode enters breakdown. A very large current suddenly flows, generating heat that can damage or even destroy the PN junction. So that's the basic idea of how a diode works, from its one-way behavior in a circuit to what's happening inside the PN junction. In the next videos, we'll explore diode applications in more detail. Thanks for watching, and I'll see you in the next video.